Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
Looking at virtual work for this particular problem, I want to determine the equilibrium position, okay, uh, uh, theta, as well as to determine the stability for the position theta. So to solve this problem, we determine the potential function, differentiate it, and set it to zero to determine theta, and as well as take the second derivative of the potential function with respect to theta as well, and plug in equilibrium position, okay, that will either go the theta and solve for the stability, determine the stability for this member. Okay, let's call it AB, and the length is given. And let's call here AC, and the length is given. Okay, and this is theta as well. Let's call here C. All right, and we have the spring. So where it is somewhere where it is. So let's say we have the spring force F starts with S, and the displacement okay, S, and something like that. We have F, so with S, and the displacement. Okay, now we have the distance between here and somewhere where the spring is hooked. Yeah, call it distance is given. Okay, 0.5 meters. All right. So if we, and this is W, so let's call this W, and from the datum AC, we can determine the height. Okay, let's call it Y, which goes for the member BC as well. It has the same weight and length, so we just call it W. All right, so that if we the spring stiffness is also given, if we consider the spring, we are going to have S, let's call the stiffness S. So it's going to give us uh, S, sorry, it's going to give us 2 into cos 0.5 cos theta, because each of those members, AB and BC, are zero point 0.5 in length, 0.5 meters in length. Okay, cos theta, okay, then minus this 0.5 meter there, okay, okay, minus 0.5 meters. To do that, we have this, and of course, minus 1, the original length of the, uh, sorry, 0.1 is 0.1, the original length of this spring when it is unstretched. So we'll have it to be 0.1 meter from 100 mm, converting it to meters. So we'll have that, so that we can just make our S to be equal to, so if you do your mathematics, it will give us cos theta minus 0.6. Okay, all right. So we can now determine, all right, the potential, sorry, the elastic potential energy is going to give us call it this source with E is equals to F S times the displacement over 2. This is also the same thing as the spring stiffness, the displacement squared over 2. All right. So that for the bars, we consider the bar, we are going to have Y is going to give us equal to half because the weight will definitely uh, up to the middle, okay, of the bar, considering it being uniform, so that we have this sine theta for one bar, for one of the bars rather, so that the gravitational potential will give you equal to, actually we are going to have it to be uh, positive. It's going to be positive because it is above the center of gravity of the bar is above the datum AC. All right, so that for the potential function, we can now have W uh, Y for the first bar AB, and for BC we have W Y as well. All right, then plus our spring. Our spring is K S squared over 2. So we have this. So we cannot plug values into this. We plug values into this that we have gotten. We already know what that each of the mass. Remember, AB and BC has a mass of 10 kg. If you multiply them by 9.81, we are going to arrive at 98.1, multiplied by our by the what we got as okay the displacement, right? The height rather will arrive at this. So we're going to have something like 98, okay, 0.1, okay, okay times 0.25 sine theta, okay, 0.25 sine theta plus, of course, is we are going to have it the same thing. So we can just say it's something as two times for both of them, since they are the same thing, having the same magnitude. So we can just say it's 2 times what we have for 1, okay? So no need to repeat it again. So we have that, all right? So that we can have then for the spring, it's going to give us 1,500. The spring constant is given as 1.5 kilonewton per meter. So it's equal to 1,500 newton per meter, all right? So that we have to multiply this by what we have as a S. We are going to have this to be cos theta, okay, minus 0.6, all right, squared. So that if we bring out everything here, we are going to arrive at this one to be V to be equal to 49.06 sine theta k plus 750 Okay, cos square theta, cos square theta, okay, minus 900 cos theta, cos theta plus 270. So we can just differentiate this now to determine the position function. So to take so to determine the equilibrium position, okay, theta, we have this. It's going to give us set it to 0, give us give us 49.06 cos theta cos theta minus 750, okay, sin 2 theta, sin 2 theta plus 900 sin theta, 900 sin theta. If we set to 0, now if you solve this particular problem, of course, sin 2 theta is 2 sin theta cos theta. Okay, having that in mind, to solving the problem, okay, we are going to arrive from trial and error that theta is equal to 4.7 degree, okay, and theta is also equal to 5 point it's equal to 5.21, sorry, 51.2 degrees. Okay, now if you take the equilibrium, if you take consider stability and take the differentiate further the second time with the potential function, we are going to arrive at for theta. To do that, we are going to arrive at 49. Okay, just follow the same procedure, okay, to determine the okay. Oh, yes, sorry. We're going to arrive at minus 49, okay, 0.06 sin theta, sin theta minus 1500, okay, cos 2 theta, cos 2 theta, okay, plus 900 cos theta, plus 900 cos theta. So if you take the second derivative for when theta is if you plug in when theta is 4.7 degrees into that, we are going to arrive at minus 5 5 8 6.91.91, which is less than 0, which is less than 0. Okay, you can see at that position it's unstable equilibrium. Then when theta is equal to 51.2 degrees, we are going to arrive at 847 47.81. You can see that it's clearly greater than 0, so this is stable equilibrium. So these are the equilibrium position and their stability.